All right, so in our next section, we're going to take a look at 5.6, which is rational functions. So what is a rational function? Well, if you think about a rational number is one that can be expressed as a fraction. The same thing, rational function is a function that can be expressed as a ratio or a fraction of two other polynomial functions. So here f of x equals, for example, g of x divided by h of x, where g and h are both polynomial functions. The domain of the function f then consists of all real numbers except for solutions or zeros of the denominator. That would cause division by zero, thus causing an error or an issue that we're going to have to address here in a bit. And what that division by zero is going to cause or force to occur in our function is we're either going to have what's called a vertical asymptote, where our graph is either going to go to positive or negative infinity in terms of the y values as it approaches a particular value, or we're going to end up with a straight up hole in the graph. We're going to have one spot that's literally missing. It's not there. So we're going to talk about where both of those come from and why and what causes them. So let's take a look. I have a couple of rational functions here, and I have domains listed below for them. So here f of x is 1 over 2x minus 3. If I were to set that 2x minus 3 not equal to 0 and I solve it, I would get that x cannot equal positive 3 halves. Thus, I have the single break in my domain at positive 3 halves. So I have the union of two sets. It's going to be negative infinity through 3 halves, non-inclusive. So everything up to but not including 3 halves. And then 3 halves non-inclusive through infinity. So again, everything coming down to 3 halves, but not including 3 halves. So literally the only value that's excluded is 3 halves itself. Same thing here in g. If I were to factor this, right, for my denominator, I end up getting that x cannot equal negative 2 and cannot equal negative 1. Thus, I have 2 splits in my domain, right? So however many restricted values or restricted points we end up with in our domain, we're going to have the number of restricted values plus 1 intervals in my domain when we write it in interval notation. So again, I have negative infinity through negative 2, non-inclusive, negative 2 through negative 1, and negative 1 through infinity, again, all non-inclusive using parentheses. The last one, which I guess really probably should be an h of x maybe, all right, just for the sake of the slide. I have x squared plus 9. If I were to set x squared plus 9 not equal to 0, I would get x squared cannot equal plus or minus 3i. Okay, those are not real numbers, they're imaginary. Therefore, in the real numbers, I have no values that cause division by 0. Thus, my domain here is going to be all real values. So, I mentioned that we're going to have something called vertical asymptote. So what in the world is a vertical asymptote? So by definition, it's a line. X equals a is a vertical asymptote for a graph of the function if the function f of x approaches infinity or approaches negative infinity as my x values approach some number, right, that x equals a, that vertical line, from either the left or from the right. And here this little negative or plus there written above the a means from the left or from the right, and this arrow means approaches. So x approaches a from the left, okay? So what we're having is as my graph gets really close to that value x equals a, right? My graph itself, the y values f of x, are either going to positive or negative infinity. What's really happening is I get closer and closer to dividing by 0. And as I get very close to dividing by 0, I'm dividing by a smaller and smaller amount. And if you think about writing that as a fraction, when you divide by a fraction, it's the same thing as multiplying by the reciprocal. So as I start dividing by a smaller and smaller fraction, and an increasingly smaller fraction because it's approaching 0, right? Multiplying by the reciprocal, right? Now what I'm really doing is I'm multiplying by a value that's increasing without bound, and I'm getting closer and closer and closer to multiplying by a value that's either positive infinity or negative infinity. Thus, my graph ends up going to either positive or negative infinity. I can't define positive or negative infinity, so we end up with a vertical asymptote. Okay. So again, what it really looks like, we can do this in class, but if you're really curious, go in, put this function in, and have your table set start at x equals 1, which is where our vertical asymptote is going to occur here. Right, we're going to have something that we're going to end up with a vertical asymptote here at x equals positive 1. And I'm actually going to have a horizontal, but we haven't talked about those yet as well. That's going to be the x-axis. And I'm going to have something that's going to look something like this. All right. My graph's going to look something like this, and you can look at what happens specifically to these y values as you get closer and closer to that x equals 1 point. Okay? You're either dividing by a value that's very, very, very small but negative, thus you're multiplying by a negative infinity, or you're dividing by a value that's very, very, very small and positive, thus multiplying by a positive infinity. Okay, we can take a look more at that in class, but as a general explanation of what's happening, that's what's happening. Okay, so horizontal asymptote. So there's a line y equals c is a horizontal asymptote for the graph of the function if the value of my function approaches that, so f of x approaches c, right? As my x values either become infinitely large or infinitely small. So as x approaches infinity or negative infinity. Okay, so what I'm talking about with the horizontal asymptote, I'm talking as essentially the left and right arrows of my graph go off into the distance, okay, to the left and the right, if you will. Okay, so if we look back here, I'm talking what's happening out here, right? This graph is going to get closer and closer and closer and closer to 0, but it's never actually going to get there. Think about in this particular instance why that's happening. Here I've got 1 divided by, and as x gets bigger and bigger, I have a positive value being divided by an infinitely large value, right? Even though it's only 1 divided by a very large number, I still get strictly positive values. I never actually get to 0. Okay, so even though I'm dividing 1 by really, really large values and I'm getting absolutely incrementally and infinitely small values as a result, they're still positive values in this case, or negative values on this end. So I never, in this case, actually get to 0. Okay, my value is always strictly going to be positive or negative. Now, horizontal asymptotes tell us what's happening out on the left and right ends as I approach negative or positive infinity. It doesn't tell me what's happening in the middle of my graph. And with that being said, not always, but at times we're going to have values or graphs where we're actually going to cross that horizontal asymptote. Okay. In terms of a vertical asymptote, I can never ever cross. I can never touch them. Okay. Horizontal asymptotes, I won't cross them as I go to positive or negative infinity, but it is possible for a graph to cross over completely, or possibly to cross it and then approach it from the other side. And we'll see what that looks like as we go through and do a couple of these graphs. Okay, so again, horizontal asymptote, my function approaches some y value c as the x values specifically approach either infinitely large or infinitely small values. So we have a theorem on horizontal asymptotes, and it is the following. So let's assume a generic rational function f of x equals n of x over d of x for the numerator over the denominator, right? And then by definition, just polynomial functions, right? Here I'm dealing with n of x having a degree n and my denominator having a degree m, okay? So what's going to be important to us here is the degree of the functions. So when the degree of the numerator is less than the degree of my denominator, then the x-axis, or y equals 0, is going to be the horizontal asymptote. And that's what happened in that very first example that I showed you guys. When the degrees equal one another, when n equals m, we have case 2, and the line that's the ratio of my leading coefficients, a sub n over b sub n, or b sub m, is going to be my horizontal asymptote. So again, case 2, when the degrees equal, it's going to be a ratio of the leading coefficients as my horizontal asymptote. In case 3, when the degree of my numerator is greater than the degree of the denominator, then we're going to have no horizontal asymptote. And in fact, what we're going to have what's going to be called a slant or an oblique asymptote, right? That's going to be y equals, and I'm going to write q of x. It's going to be the quotient of x. So I'm going to have to do polynomial long division. And what we're going to do is the polynomial long division, and whatever that quotient of x, whatever I have on top of the long division, that equation, be it linear, quadratic, or something else, whatever that equation is, we're going to have a asymptote that is not horizontal, okay? And yes, it can be a curved asymptote, so our graph could be approaching some nonlinear function with respect to the y and x values here, okay? Normally I do this in 2 days, and I think I'm going to do this in one video just to make life simpler for us in terms of our hybrid schedule at the moment. So you will see a slide later with the slant and oblique asymptotes, but for now I'm just going to put it in here. So case 3 is when the degree of the numerator is greater than the denominator, and the oblique or slant asymptote is going to be the quotient when I divide out the polynomial. So holes in asymptotes. So I mentioned earlier also that we could get a hole in the graph. So a factor can be reduced that would normally cause a vertical asymptote. So if when I factor my function, there is some factor that exists that I'm going to cancel out, I still have to account for the fact that was there and that caused the division by 0 issue. But when it cancels out, it no longer causes a vertical asymptote. Instead, it's going to cause a hole. So my example here is this. When we go through this, a lot of times we're going to have to look at functions in their factored form and in their standard form at different parts for different purposes here. So when I factored this, my numerator x plus 1 times x minus 1, all divided by x plus 1 times x plus 4. Now, obviously, you should be able to see here the x plus 1s are a common factor, and they're going to cancel out. So what I get here then is x minus 1 divided by x plus 4, okay? If I were to go and try and sketch this graph, just very, very quick, very rough sketch, right? What we're going to have is a vertical asymptote that's going to occur at x equals -4. So somewhere out here at -4, I'm going to have a vertical asymptote. So we're going to do the vertical asymptote with a dashed line. In Notability, the easiest way is do the straight line, then do the partial erase. All right. I'm going to have a horizontal asymptote because the degrees equaled at the ratio of the lead terms. So I'm going to have horizontal asymptote here at 1 over 1, or x or y equals +1. So again, I'm going to go through and just very, very, very quickly sketching this out. Okay. I am going to end up with a hole in the graph, right? Because x cannot equal -1. So what I need to do then is evaluate the reduced function at -1. So if I do that, I'm going to have -1 minus 1 over -1 plus 4. And I'm going to get -2 over 3. So at the point -1, -2/3, so -1, -2/3 is somewhere right about here, I'm going to have a hole in the graph. Right? I'm just going to put an open circle as if it's an endpoint of a graph that's not included. Because what we're going to have is all of the points coming up to, but not including this particular spot in the graph. Right? I'm going to have a graph that looks something like this. Now, we haven't really talked about why I know where different parts of the graph lie and exist. Right? This part here, I know where it exists because I have that hole in the graph. I know one specific position. Okay, we're going to talk more about how I know where things go and what this looks like, because it's going to be different at different times throughout the graph as well. Okay, so again, vertical and horizontal or vertical asymptotes and holes rather. I need to factor both my numerator and denominator completely so that I can figure out what the solutions to my denominator are. But I also need to take a look at any factors that reduce or cancel because those are going to produce holes in the graph instead of vertical asymptotes. Okay. So what I want to do here is just find the horizontal and the vertical asymptotes. So my vertical asymptotes, again, going to be solutions of my denominator. So 5x plus 10 cannot equal 0. And if I go and solve this, we're going to subtract the 10, so I get 5x equals negative 10. When I divide by 5, I get x cannot equal negative 2. All right, so I'm going to have a vertical asymptote at x equals negative 2. My horizontal asymptote, right, so n equals m. Right, for my horizontal asymptote, right, degree of the numerator is 1, degree of the denominator is 1. Therefore, my horizontal asymptote is going to be at y not equal to 1/5. Okay, there is nothing that's going to cancel here, nothing that reduces, thus we have no holes in the graph. So a vertical asymptote at x equals negative 1/2 and a horizontal asymptote at y cannot equal 1/5. Okay. Same thing, we're going to find vertical and horizontal asymptotes. Here I have two quadratics. I do need to go ahead and at least try to factor or look at factoring. Okay. If I go and factor this one, right, I'm going to end up with square root of 3 times x plus 1 and times square root of x, or 3 times x minus 1 over x plus 3 times x minus 3. So two things here. One, nothing's going to reduce, so factoring the numerator really didn't help me in this sense. If you look at it in something simple like this and you absolutely know it's not going to factor to something that's going to cancel, then you don't necessarily have to factor the numerator, but it doesn't hurt. We are going to have to factor the numerator later when we go to graph and completely evaluate these functions, but for the purpose of just the vertical and horizontal asymptotes, we may or may not need to do that. All right, so here my vertical asymptotes are going to come from solutions of my denominator. So x cannot equal 3 and x cannot equal negative 3. My horizontal asymptote is going to come here, and n equals m. The degree of both my numerator and denominator are 2, and it's going to be a ratio of my lead coefficients, so 3 over 1, or y cannot equal 3. Okay. Again, nothing simplified, nothing canceled, thus we have no holes in the graph, so we only have our 2 vertical and our 1 horizontal asymptotes here. All right, so again, if I take a look at this one, I have x plus 1 over x squared minus 5x plus 6. So if I factor my denominator here so I can see if we have anything that's going to cancel, all right, my denominator in this case is going to factor to x minus 6 times x plus 1 over or underneath of an x plus 1. All right, so this factor of x plus 1 is obviously going to cancel out. What it's going to leave me with is just a 1 divided by x minus 6. So in this case then, I'm going to get a vertical asymptote that x cannot equal positive 6. The degree of my numerator is less than the degree of my denominator. So what I normally would do at this point, because you haven't seen slant or horizontal asymptotes, I would say there is no horizontal asymptote. But we're going to circle back around and we're going to find that slant asymptote here in a minute. I am also going to have a hole in the graph, and that hole is going to occur at x equals negative 1. Right? So if I evaluate the simplified function then, so f of negative 1, I'm going to have 1 over negative 1 minus 6, or 1 over negative 7. So I get a hole at the point negative 1, negative 1/7. Right? Excuse me, I did that backwards here. The degree of my numerator is less than the degree of my denominator. Therefore, my horizontal asymptote is going to be the y-axis at y equals 0, okay? I had that flip-flopped in my head, and I was getting ready to set up the division, and realized that we can't even divide that because the denominator is greater than the numerator. Thus, I just set it backwards when I was doing the video there by mistake, okay? So we have a vertical asymptote at 6, a horizontal at 0, or the x-axis, and we have a hole in the graph at -1, -1/7. All right, so when we go to sketch rational functions, right, there's a lot of information that we're going to need to be able to find and plot to get a picture of what this graph may look like. And again, similar to polynomial functions, it's going to give us a lot of information, but it's not necessarily going to give us all of the information. So I'm going to be able to get a good idea or sketch a picture of what the graph should look something like, but it's not going to be perfect. Also, when we go through this process, we're going to get to the end in a lot of these problems and say, okay, I know what's happening or where the graph should be or what it should look like over particular intervals, but I don't necessarily know what it looks like over every one of my intervals. So we're going to get to the end, and at times we're going to have to test some values to come up with some of the other points that we need or some of the other information we need to graph or sketch this graph of the function. So assuming I have a rational function f of x equals some g of x over h of x, right? And there are no common factors, thus nothing that I can continue to reduce, okay? If there was something we reduced, make a note of that because you're going to have a hole in the graph somewhere that we need to find as well, okay? So step one, I want to find all of my x-intercepts, or the zeros or roots of the numerator, okay? So x-intercepts, right, are going to come from my numerator, okay? So set your entire numerator equal to 0 and solve it, right? If it's quadratic, awesome. If it's linear, awesome. You know how to solve those. If it's a cubic or higher, well, we now know how to also solve those because we just did polynomial functions, all right? Step two, find all the zeros of your denominator, all right? These and all the real zeros of the denominator, right? These are going to be our vertical asymptotes, right? So once you've found them, you're going to go ahead, you're going to plot each of those vertical asymptotes using a dashed line. And also after step one, if you show the work, go ahead and plot those x-intercept points. Step three, you're going to find the y-intercept f of 0, if it exists, it doesn't always, and plot the point 0, f of 0. So you're going to plot that x, or that y-intercept rather, all right? The nice thing is that your y-intercept is typically going to be a ratio of your constant terms if you have them. Step four, you're going to apply the theorem on horizontal asymptotes. If there is a horizontal asymptote, y equals c, go ahead and sketch that line y equals c. If you're in case 3 and you see that they're going to have a slant or an oblique asymptote, go ahead and divide the function, find the quotient, and sketch y equals q of x, right, as your oblique or slant asymptote, right? I said earlier that we can possibly cross over horizontal or oblique asymptotes, all right? Never a vertical, but we can cross the horizontal or obliques. So step 5, we're going to test for that. So whatever our horizontal asymptote happens to equal, so y equals c or possibly q of x, right? I need to set the entire function equal to my horizontal or oblique asymptote, and I need to attempt to solve for x. Okay, sometimes it's going to work out really nice, sometimes this is going to get messy. Okay, so again, we're going to, step 5, we're going to set the entire function equal to my horizontal or oblique asymptote. I'm going to cross multiply and I'm going to attempt to solve for my value x, right? Any real solutions we get are places where we cross the horizontal or oblique asymptote. If it's horizontal, it's easy. You have the point, then x comma c, okay? Because you have, obviously the y value is always c in a horizontal, and any solution you got x, so you have x, c as a point. Go ahead and plot it. If, however, you find that you cross a slant or oblique asymptote, then you need to go and evaluate the slant or oblique asymptote at whatever that x value is to figure out what the y value of the function of the oblique asymptote is at that specific x value. Again, if you have that case, go ahead and plot it, all right? And in step 6, we're going to go through and we're going to sketch our function. At this point, we know we're always bound between and bound by our vertical asymptotes. I can never cross them, okay? Like they're the walls of an impenetrable fortress, okay? We can't get over them, can't get in, can't get out, okay? We are bound by them. We know where we are able to possibly cross the horizontal asymptote from step 5, okay? So we're going to essentially sketch our graph based on the x and the y-intercepts and any of the points that we have, whether they're above or below the horizontal or oblique asymptotes over the particular intervals that are bounded by those vertical asymptotes. And unless we cross, we're bounded left, right, top, or bottom by all of those asymptotes, okay? There are going to be points where maybe you know you cross between two vertical asymptotes, you cross a horizontal, but you don't know whether you cross in a decreasing fashion or an increasing fashion. Then what I'm going to have to do is pick a value between that point of crossing and one of those two asymptotes to see, am I above or am I below at that point? And then we're going to sketch the function either increasing or decreasing, whatever the case may be. There could also be intervals where, you know, to the right of the rightmost vertical asymptote, for example, maybe I don't know whether I'm above or below the axis. So if it's, say, x equals 5 is that last asymptote, I need to pick a value that's larger than 5. So maybe x equals 7. And I want to evaluate the function at 7 and see what I get. If I get something that's above the asymptote, then I know I'm bounded to the right of that asymptote and above the horizontal. If I would get something below it, then I know I'm bounded underneath. Okay, so when we get to that very last step, we're going to sketch what we got, and we're going to test where appropriate or where necessary to figure out where the heck we got to be. So to recap this slide, and there's a lot going on here, so probably want to screenshot this one. All right, x-intercepts are solutions of my numerator. Vertical asymptotes and holes are solutions of my denominator. If, when you factor everything out, you have holes, you also then need to go and evaluate the reduced function at that x value of the hole to figure out that point as well. The y-intercept f of 0 is the ratio of the constant terms. You're going to apply your theorem on horizontal asymptotes. You're going to plot it. In step 5, you're going to test to see if you cross that horizontal asymptote by setting the entire function equal to c, or possibly the oblique asymptote, and you're going to attempt to solve for x. All right, step 6, you're going to sketch whatever it is that you've got and test where necessary. All right. So that all being said, let's do this. All right. So step 1, right? If it needs factored, I'm going to factor it here. In this case, they're both linear functions, so I don't need to do anything with it. So step 1, I'm going to find my x-intercepts. X-intercepts, again, are going to be solutions of my numerator. So here I'm going to get a x-intercept of 1/4 or the point 1/4, 0, right? If I solve 4x minus 1 equal to 0. All right, so I'm going to go ahead and I'm going to plot a point there. Okay, I'm going to try and get as close as possible. Step 2, right? I want to find my vertical asymptotes. Okay, these are going to be solutions of my denominator. So if I set that denominator 2x plus 3 not equal to 0, I'm going to get that x cannot equal -3 halves. So at -1.5, right, I'm going to have a vertical asymptote. Again, I'm going to sketch that in. I'm going to come back with the partial erase feature here in Notability, and I'm going to graph it, right? If you're doing this on paper and pencil, a ruler is going to be really helpful for some of this, just to sketch in that dotted line and to do so neatly, okay? Step 3. Step 3, we want to go ahead and we want to find our y-intercept, right? My y-intercept, I'm going to evaluate f of 0, right? When I evaluate f of 0, this term's a 0, this term's a 0. Any term that has an x in it becomes a 0, and we essentially get a ratio of the constant terms is the only thing left over. So here it's going to be -1/3, or we have the point 0, -1/3. So again, I'm going to go ahead and I'm going to plot that point. I know it's not quite at 1/3 there, but I'm going to try and get as close as possible. Okay. Step 4, I'm going to apply my theorem on horizontal asymptotes. Degree of my numerator is 1, degree of the denominator is 1. So n equals m. And because we're in case 2 of that horizontal asymptote theorem, I have a horizontal asymptote then that occurs at y equals the ratio of my lead coefficients, or at y equals 2. So again, I'm going to go ahead, I'm going to sketch that horizontal asymptote in. I'm going to go back with the partial erase feature, and I'm going to go ahead and make this line dotted. Okay. Step 5, I want to test. Do I ever cross that horizontal asymptote? So I'm going to set my entire function, 4x minus 1 over 2x plus 3 equal to 2, and I'm going to attempt to solve. So if I cross multiply here, we're going to get 4x plus 6 equals 4x minus 1. And if I subtract 4 on both sides, I get 6 equals negative 1. Well, 6 doesn't equal negative 1. That's ridiculous. This is not true. Therefore, there is no cross. Okay? So now what I want to do in step 6, I want to go ahead and graph my function. Now, what I was talking about earlier is being bounded. Okay? You look, I have a vertical, which I can never cross, and a horizontal asymptote that I just demonstrated that we don't, in this case, cross. I have a couple of points here. Right? I am bounded by these two asymptotes in this interval that's greater than 3/2 or negative 3/2. So I'm going to end up with a graph that's going to look something like this, right? Think about if you were walking around a room, right? You don't necessarily walk into the corner, make a 90-degree right turn, and turn to the right, okay? You're going to round that corner off. You're going to make it nice and smooth, and we're going to get a graph that maybe, in this case, if I can draw it without being on the line, it's going to look something about like that. That was terrible. Let me try it again. All right. So we're going to get something that looks like that. Okay. And in both cases, in the vertical and the horizontal, I'm going to approach, I'm going to get close to that asymptote. I probably don't want to actually like touch it per se, but get close. You don't have to get super crazy close, but you don't want to be too far away. Now, the other problem that I run into here is I have absolutely no idea what's happening in this interval left or less than negative 3/2. So what I need to do in step 6 here is I need to test a point, right? I can pick any x value that's to the left of that, or in this particular interval from negative infinity to negative 3/2. Let's do something easy. Let's use like negative 2, right? So let's evaluate f of negative 2. F of negative 2, right, if I go and plug this in, I'm going to have 4 times negative 2 minus 1 over 2 times negative 2 plus 3. So I have negative 8 minus 1, or negative 9, over negative 4 plus 3, which is going to be negative 1, so I have positive 9. So at negative 2, I'm going to be up here at positive 9. Again, I'm bounded by these asymptotes. Since I'm above the horizontal asymptote, then I know that my graph must look something about like this. Okay. And congratulations, we've graphed our first rational function. All right, let's go through and do a couple of these because this is one of those where repetition is kind of key. Okay. So second example, f of x equals x plus 1 over x squared plus 2x minus 3. So again, first thing I'm going to do, I'm going to go ahead and factor my numerator and denominator if possible. So the numerator is just x plus 1. My denominator here is going to be x plus 3 times x minus 1. So main thing I notice here is that nothing is going to cancel out. Okay. So step 1, solutions of my numerator, right, are going to be my x-intercepts. Solutions of the numerator, I'm going to get x equals negative 1, right, or the point negative 1, 0 as my x-intercept. Step 2, solutions of my denominator are going to be my vertical asymptotes, right? So we're going to get that x cannot equal negative 3 and x cannot equal positive 1. So again, I'm going to go ahead, I'm going to graph them in. Kind of missed there a little bit. We'll get that in a second. There we go. It's a little better. All right. And I'm going to go through partial erase. All right. And I'm going to make this, or these both, into some dashed lines. Okay. Step 3, I'm going to evaluate and find my y-intercept. So I'm going to evaluate f of 0, and f of 0 in this case is going to be 1 over negative 3, or we get the point 0, negative 1/3, right? So I get a point somewhere about here. Okay. Step 4, we're going to evaluate our horizontal asymptote theorem, all right? And in this case, the degree of the denominator is greater than the numerator, so the numerator is less than the degree of the denominator. Therefore, right, the 3 dots mean therefore, I have a horizontal asymptote at y equals 0. So I'm going to have my x-axis, right, as my horizontal asymptote. Okay, and let me adjust this just a little bit, maybe. There we go. All right, and I'm going to go through again. I'm going to make this dashed. All right, when it's on the x-axis, it's a little bit harder to see everything, but it is still there. Okay. Step 5. Step 5, I'm going to go ahead. I'm going to test. Can the function equal that horizontal asymptote? Okay, so what we're going to see, I have x plus 1 over x squared plus 2x minus 3. If I cross multiply, I'm left with 0 equals x plus 1, or x equals negative 1. Well, didn't I already have the point negative 1, 0 in this case? And I actually already have that plotted over here as well. So I know there's at least one point at which I touch or cross the horizontal asymptote. So I cross at x equals negative 1 here, right? Again, I could have already seen that from the graph, so I did know that, okay? In this case, you're crossing and not touching, okay? So you are strictly going to cross the horizontal asymptote, which is kind of important for us here in step 6 when I go to start sketching. So let me zoom in here a little bit. Since I know that I'm crossing, I know that I cross, and then as I'm moving left to right, I have a point down here that's below, which means my function's decreasing on the interval between the negative 3 and 1 here. And because it's decreasing, I know then it has to start up here and kind of look almost like a cotangent function, or an opposite of a tangent, or even in this case, the opposite of an x cubed function. So it's going to look something possibly about like this. Okay. So I've got one interval in my graph taken care of here. The problem is I don't know still what's happening out here or out here. So what we're going to do, we're going to test some values, right? And in this case, let's test f of, let's do like negative 5, right? So if I plug in negative 5, and I'm going to do this a little bit quicker, I'm going to have a negative 4 over a negative 2 and a negative 6. So I'm negative 4 over 12. Excuse me. Negative 4 over 12, or we're going to have a negative 1/3. All right, so at negative 5, I'm at negative 1/3. All right, so negative 5, negative 1/3. I've got a point somewhere here. Again, I know I don't cross the axis anywhere out here in this interval less than negative 3. So I'm bounded by my two asymptotes. Then I'm going to get a graph that maybe looks something about like this out here. Okay. I also need to know what's happening greater than the positive one. So let's test, I don't know, let's do f of 3. Okay. So I'm going to have 3 plus 1, or 4 over 3 plus 3, which is 6, times 3 minus 1, which is negative 2. So here, ironically, I'm going to get 4 over negative 12, right, or negative 1/3. I didn't plan that. So 3 and negative 1/3 is that point. Let me look here for a second, because I was thinking that that shouldn't be, or I do the other one incorrect. Oh, yep, I did make a mistake there. This should be a positive 2. all right, which makes this a positive 1/3. All right, I knew there was an issue based on the shape of the graph. I knew something was wrong there, that I made a math mistake in one of the two test points. All right, so here again, I'm now bounded by those axes. When you get something that we're going to try and round off, although it's really, really close to the axis already where we tested, but it's going to look something about like this. Okay, the one thing that kind of triggered or caught me off guard, and I knew I had made a mistake, is that here I knew that my tails on the other sides or alternating sides of each asymptote should be going in opposite directions, because each of the asymptotes, we didn't really talk about this yet, but each asymptote only occurs once, has a multiplicity of 1, therefore they're going to be alternating. If, however, let's say that the x minus 1 factor occurred twice, then the x equals 1 asymptote is going to occur twice. And then what we would have had is tails on the same side, both at negative infinity or both at positive infinity, when that asymptote occurs an even number of times. So in this case, because I knew they occurred an odd number of times, I knew that they should alternate in directions. They shouldn't be same direction tails. So I knew I had made a mistake there. And again, all those little things, you're always checking to make sure that you didn't do something silly. And sometimes it's a negative sign, or, you know, in that case, I just literally added it wrong and said it was negative instead of positive. Okay. So always, always, always with these, be checking to make sure you're not making silly little mistakes. Let's do another one here. All right, so I've got f of x equals x squared minus 25 over x squared minus 3x minus 4. Again, very first thing I want to do, I want to go through and I want to factor. Okay, so you're going to get x plus 5 times x minus 5 over x minus 4 times x plus 1. Again, in this case, I notice that nothing is going to cancel, so step 1, we're going to go to my x-intercepts. All right, I'm going to get x equals plus or minus 5, or I'm going to have 5, 0, and negative 5, 0. I'm going to go ahead and plot those points right away at negative 5, 0, and at 5, 0. Okay. Step 2, my vertical asymptotes. Vertical asymptotes are going to occur, x cannot equal 4, and x cannot equal negative 1. So again, I'm going to go ahead and I'm going to sketch those in. Again, those are my solutions of the denominator. All right, and I'm going to use that partial erase tool to make them into dashed or dotted lines. All right, step number 3 then, we're going to find my y-intercept. So f of 0, it's going to be the ratio of the trailing coefficients, so negative 25 over negative 4. Which is going to be 6.25. So we're going to have 0 and positive 6.25. So I'm going to have a y-intercept somewhere right about here. Step number 4, right? Degree of the numerator equals degree of the denominator. Therefore, my horizontal asymptote is going to occur at the ratio of the lead coefficients 1 over 1, or simply at y equals 1. So again, I'm going to go ahead and I'm going to sketch this in, all right? I'm going to adjust that just a little bit. There we go. And again, we're going to make it a dashed or dotted line here. Okay. Step 5. Let's take a look and see, do I ever cross that horizontal asymptote? So I'm going to set 1 equal to x squared minus 25 over x squared minus 3x minus 4. If I cross multiply, I have x squared minus 3x minus 4 equal to x squared minus 25. Then if I attempt to solve, when I move my x squareds over or subtract x squared, they cancel. If I add 4 to both sides, I'm going to have negative 3x equals negative 21, or x equals 7. So since I get a solution, I know that I'm going to cross at the point 7, 1. So at the point 7, 1 right here, I'm going to cross that function. Okay, so let's go ahead. Let's in step 6, let's try and sketch this if we have everything we need. So again, think about we're bounded. Okay, I know I can't cross my verticals, and I know the only place that I cross my horizontal is here at 7, 1. So in my leftmost interval, right, I have a point that's below the horizontal asymptote, so I know I'm bounded below, and I'm going to end up with a graph that's going to look something maybe about like this. Oops. In step 2, okay, I know that here in this, or in the second interval rather, not step 2, I know that I have my y-intercept and a point between the two vertical asymptotes that is above the horizontal asymptote. I also know that I never cross that horizontal asymptote, so in this case I have to get some U-shaped graph that occurs inside of this interval. So maybe we get something that looks about like this. Okay, and in that last interval, right, I know that here I have a point when I'm working from left to right, okay, that I'm below my asymptote, okay. I know I cross it at this point, so I must cross and go above, and then I'm going to approach the asymptote from the other side, right. So we're going to get something then that might look about like this. Okay, so you're going to get something that almost looks like, you know, the hump on a camel's back, all right, where we're going to cross from one side to the other, all right, and when I cross the asymptote, then I'm going to come back to and approach the asymptote from the other side from which I had started, okay. Make it obvious that you crossed the asymptote. One thing I don't want you to do, okay, is do something like this. Because at that point I have no idea whether you crossed or whether you didn't. Make it clear for me, right, that you came past that point, okay, crossed over, and then approached it from the other side, all right. So we talked about oblique asymptotes, right? That's when the degree of my numerator is greater than the degree of the denominator. We're going to get an oblique or a slant asymptote and the quotient of that function. So I'm going to divide the function f of x, and I'm going to see what the quotient actually is going to be my oblique asymptote. So the example that we're going to do here is the following. So I have x squared plus 3x plus 2 equals x minus 2. So I still need to go through the same process. I still need to factor my numerator and my denominator so that I can look to see if anything cancels, and I can also come up with all of my different pieces here in my 6-step process. So we're going to have x-intercepts at -2 and -1. I'm going to have vertical asymptotes at x cannot equal +2. My y-intercept is going to be at 2 over -2 or -1, so 0, -1. Now, step 4 is where the fun happens here. Okay, step 4, I've got n greater than m. Therefore, I'm going to have an oblique asymptote. Right, and it's going to be at y equals, and I need to figure this out. So let's come off over on the side, and I'm going to divide x squared I'm going to divide x squared plus 3x plus 2 by x minus 2. Okay, so dividing lead coefficients, x squared divided by x gives me x. I distribute, I have x squared minus 2x. I'm subtracting this entire line, and we end up with 5x. I bring down the next term. I divide lead coefficients. 5x divided by x gives me 5. I multiply, I have 5x minus 10. Right? I subtract this entire line, and I end up with a positive 12. So my quotient then is up here on top. My quotient of x is x plus 5. And you might be saying, well, what are you doing about that remainder of 12? Remainder of 12 doesn't matter here. right? I'm not looking for a factor, okay? So the remainder of 12 doesn't affect the outcome here in any way, shape, or form. And to be totally honest, if you got a remainder of 0 here, then you probably had something that should have reduced and or possibly made a mistake, okay? So you should expect to get a remainder here, but what's important to us is this quotient up here on the top, okay? So let's go ahead, let's test it real quick first as well. So I'm going to test, and I'm going to set x plus 5 equal to x squared plus 3x plus 2 over x minus 2. If I cross multiply and distribute, I'm going to have x squared plus 3x minus 10 equals x squared plus 3x plus 2, or I'm going to end up with negative 10 equals 2, therefore no cross. Okay, simplifies our life. So let's go ahead, let's sketch a couple of these things in because I didn't do it along the way. So I'm going to have x-intercepts at negative 2 and also at negative 1. I'm going to have a y-intercept at 0, negative 1. I'm going to have a vertical asymptote at positive 2. Again, let me adjust position here a little bit. All right. We're going to go ahead, we're going to make a dashed. And I'm going to have a oblique asymptote at y equals x plus 5. So I'm going to have something right about like this. And again, I'm going to go through and I'm going to make this into a dashed line. Okay. Now, what I know at this point, and let me also, ahead of time, I'm going to duplicate this. I'm going to extend, if I can, the line here a little bit. Okay, I'm going to do the same thing here. All right, just so that we have the room. All right, again, I know I'm bounded still by that vertical asymptote, and because of step 5 here, I know that I never cross my oblique. So I have multiple points here, and again, I know that I can't cross any of them. I'm bounded below and to the left of these asymptotes, so I'm going to get something that roughly is going to look like this. And again, we want to make these smooth graphs. They shouldn't have any sharp points or any corners. I know based on the fact that this asymptote really has a multiplicity of 1 that I should alternate and be above, but let's test and make sure. So let's evaluate maybe f of, let's do 4. Okay, so here I'm going to have 4 squared or 16 plus 4 times 3 are 12 plus 2 over 4 minus 2, which is 2. All right, so here I have 30 divided by 2 or 15. All right, so I know I'm going to have a point somewhere way up here. Okay, and again, I'm going to be bounded by these asymptotes. I'm going to get something that maybe looks like that. Oops. Okay, so maybe it looks something like this. All right. So what I want you guys to do, all right, there were a couple of other slides that I took out of the slideshow for the video. I want you to go back and at least try 1 or maybe 2 of those problems. All right, I'm going to have a couple of them for us to do here in class tomorrow, and we're going to take a look at a few things. We're going to do a few of these together to make sure we're on the same page. Again, each one of these graphs is going to be a little bit different, but at the same time, I think once you understand the process, once you become comfortable with that 6-step process, these really aren't that bad. It's just a matter of you have to kind of go through the steps. They're probably going to take up the majority of a page of work, and they're going to look worse than what they really are. Okay, they're kind of like a big old Rottweiler that looks mean and snarly, but it was really a big old teddy bear that just wants to cuddle up next to you and lick your face. Okay, they're really not as bad as they look. All right, so try 1 or 2 of these tonight. When you come in tomorrow, hopefully we'll see where we're at. Whether you have questions, I can answer them. We can do a couple of these together and make sure everybody's feeling comfortable before we move forward. All right, have a good night, and we'll see you tomorrow.